All right, I'm going to announce the next speaker with a little bit earlier than the schedule because there is a delay of the stream. So we have Suraj Kandpal from Intel presenting remotely on content protection on Linux. And I think we'll start in a minute. So stay tuned. Hopefully everything works.
I mean, I know there's a little bit delay with the stream and the remote here, so I think let's get started. So to start with, good morning, good afternoon, good evening, everybody, and it's great being here on XDC today. And welcome to everybody who's attending this event remotely or in person. So I'll be speaking on content protection on Linux today. And before we go ahead, just a little more about me. So my name is Suraj Kandpal, and I've been working as a graphic software engineer at Intel since 2021. And I've been working on display driver development on i915 and XC driver, where my major focus has been on HDCP, DSC, a little bit on DP, and worked on a little bit of EDP backlight management. Other than that, this is also my first XDC presentation, so apologies in advance if I mess up my presentation here and there. And over that, I'm already remote, so yeah, I guess have a little patience with me. So let's move ahead to agenda on what I'm going to talk about today. It's going to be about the what and why of content protection. Then we'll go to see the different flavors of content protection that there are there. I'll be talking about HDCP, which I work majorly on, the different versions of HDCP, why we moved from 1.x to 2.x, and then we'll come to the main spice of things and how HDCP works from user space to driver, what the user space needs to set to get driver to start enabling HDCP for you. We'll also be talking about PAVP, protected audio video path, and how it works in tandem with HDCP. We'll also be discussing the challenges and downsides of content protection. And after that, we'll have a look at what upcoming projects we are working on and what could be next for HDCP. So, with that, the what and why of content protection. So, content creation comes with a price tag. And I don't know, there's this weird thing that people have that once they invest money on it, they just don't want to give it out for free. So, yeah, with the increase in content and the quality of content and with the resolution increase, you really don't want it to be, distributed illegally or pirated. So there are a lot of mediums now through which content can be delivered to you. There's internet, there's wired medium, there's wireless medium, and a lot of ways to pirate it now. So just to give some examples, there would be a hardware device that could be basically recording your pixel stream that goes from your machine to your monitor, or there could just be a simple screen capturing app which copies whatever is being displayed over your screen. So content protection comes in and makes sure that this content is being delivered to a legitimate user without basically having it being, stolen from you or being uh, redistributed later for nefarious purposes. Next, we come to the types of content protection. We will be majorly talking about in this presentation about HDCP and PAVP. But before we move ahead to that, I would like everyone to know the different kind of content protection that is already there and all the things that come together to make this environment safe and secure for everybody. So let's start with software copy protection, which basically uses your product keys and license checking, which is basically just having a software that you have and it gets activated based on a valid product key that you are given. And once this key is used, it is invalid and cannot be used again. So if you had the games that you used to previously play, right, you needed this product key to get it activated and or to play it. So that's software copy protection for you. Then came broadcast and streaming, which is your pay for what you watch TV, cable TV provider sort of service that came in, which used CAS, which is conditional access system, which internally used ECME and EMM. But to summarize, what it does is it makes sure the subscriber gets to see the channel that they have selected and the quality that they have selected based on what they have paid for. So you would like, this is what paved the way for pay for what you watch sort of model that you see today that has been going on in OTTs. Then there is watermarking, where the content is available, but you enter a visible token or identifier. So let's say you have an image and you just write your name right on top of it. And if anybody wants to use it, either they pay you and then use it, or they just use the image the way it is and they just have that big name of yours or big identifier of yours on their website. There's forensic watermarking, which you cannot see it on the visibly on the image or content, but it can be tracked in case it gets redistributed without your permission. Then there is encryption based content protection, and this is majorly CSS, which is content scrambling used on DVDs. Then you had AACS, which was advanced access content system, which was used on Blu-rays. Then came DTCP, which is still being used on internet protocols here and there, basically digital transfer of data. Wherever digital transfer of data happens and you want to encrypt that. Then you have DRM. You do not want to confuse this with the direct rendering manager that we have. DRM stands for digital rights management, and this is implemented on the player level. Every company has its own implementation. So Google has Widevine, which is used on Android and Chrome players. Your Apple has Fair Play, and Microsoft has Play Ready. So DRM controls on what device what can be watched and how it is watched. So if you press that play button, it starts the license checking with the OTT platform on top. And if the license works out, it sets up a secure environment for you on which your content can be consumed. And this secure environment that I talk about will be talked about later. But spoiler warning, it's PAVP or protected audio video path that it enables. Then we have hardware assisted content protection, which is where we offload all the encryption and decryption work to the hardware, and software sort of becomes a messenger in between, not keeping track of what values or what keys need to be here or there. So just letting hardware take care of it. So that is your hardware assisted content protection. So moving on to HDCP, the crux or the main topic of my presentation here. So what is HDCP? HDCP, or high bandwidth digital content protection, it basically makes sure that whatever medium through which you are sending your content through is encrypted and no one in between can steal it. So it works with wired or wireless connectors based on the version. So it works on DP, HDMI, DVI connectors. And when I talk about versions, there are two of them, or two major versions of them, HDCP 1.x and 2.x, which we will describe or which we will talk about a little more in depth later. Let's talk about the topology and what all devices come inside this HDCP architecture of sorts. So you have your source, which is the one who is actually transmitting your data or transmitting the content. Then you have your sink, who will be consuming this content. So your TV or external monitor becomes a sink. Then you have your repeater. So that could be hubs, which basically are used to connect multiple monitors. So that's these are the three main HDCP devices. And when I talk about HDCP device, one thing to mention here is, if you want to become an HDCP device, first you need to get certified. So you will have to go to DCP, which is the governing body of HDCP, the ones who made the HDCP spec, and get your hardware fused with HDCP keys and certified it so that your device actually has the permission to take part in HDCP authentication to begin with. Now, who all are the major stakeholders when it comes to HDCP? So obviously anyone who's manufacturing your sink, so monitors or TVs, so Sony, Samsung, LG, Dell. So these are the people who have to implement HDCP on or algorithms on their hardware. Then you have the source manufacturer, so Intel, AMD, Nvidia, Apple. They have to do it. Then there are your DRM stakeholders, so Apple, Fairplay, Google's Widevine, and Microsoft's Play Ready. And you already have your OTT, who are the distributors of the actual content. So that would be your Netflix, Prime, Disney Plus. So yeah, this is the overview of HTCP. Now, let's talk about the different versions of HDCP. Rather than doing a face to face comparison on what is different, I would like to talk about how HDCP 1.x failed and what 2.x did better. So, why did we have to move? HDCP 1.x got broken. So, you don't want to use a broken algorithm, do you? And that was the major reason we shifted. But we already started, everybody started feeling the need for better uh, standard for content protection. The reason was HDMI 1.x was created with HDMI, DVI, all these old connectors in mind. So it didn't take into account the increase in bandwidth that came on later or the high resolutions that came on later, which also explains why it was not working well later on. It also used older and weaker algorithms. Not to say that it was HDCP 1.x's fault. It was that at those point, at that point when it was conceived, the stronger algorithms did not exist and came into existence later. We also had it not optimized for low power, and low latency use cases, and it became very bad for wireless when it came to the wireless use case. So then a decision was made to move to HDCP 2.x, which took into account your type CDP and HDMI 2.0, the benefits that came with it, and the higher resolutions it supported, the higher bandwidth it supported. It used better algorithms, and it introduced something called as a revocation list, which is basically a list of devices which end up being broken, or everybody knows that this is a weird or buggy device and is vulnerable to attacks, so you do not even authenticate that device to begin with. It introduced two types of content, that is type 0 and type 1 content. And type 0 and type 1 content were majorly introduced, or the differentiation was majorly done so that we could backward it becomes backward compatible with HDCP 1.x, because even though it was broken, we didn't want to leave HDCP 1.x people hanging, right? So we really wanted to make sure that they could keep authenticating their device, much be it at a lower resolution. So type 0 can at max authenticate 4K resolutions with a lower refresh rate, while type 1 content can go up till 8K with and HDR at a little higher refresh rates. So that's the difference between type 0 and type 1. One thing you need to know is type 0 can be authenticated by HDCP 1.4, but type 1 cannot be, while HDCP 2.x can authenticate with either type 0 or type 1 content. Now, moving on to HDCP, from user space to driver, what the policy is for the user space, what the policy is for the driver, what driver does. So to begin with, let's define user space here. It would be anything above the middleware layer. So how does it interact? So it has two major properties. So you have your content protection and content type that the user space needs to set. So let's talk about content type first. User space cannot dictate which protocol will be enabled by the driver. So it sets its content type. So it can either set it to type 0 or type 1. It's if it sets it to type 0, its driver's policy, if HDCP 2.x is available on both the source and sink, it will try to enable HDCP 2.x. If that fails, it falls back to HDCP 1.4. If HDCP 2.x is not available, then it automatically goes to HDCP 1.x. But if the user space specifies type 1 content, then HDCP 2.x is the only protocol that will be enabled by, or driver will try to enable. So now let's talk about content protection property. Content protection property can exist in three states. So you have your desired state, enabled state, and undesired state. Now, where the policy is such that the user space can set the content protection state to either desired or undesired, but never enabled. And the driver can set it to either desired or enabled, but never undesired. The reason for this is we don't want the user space having a way to enable HDCP, even though hardware has not really enabled it, which makes it vulnerable to attacks. And we don't want driver to just stop trying to authenticate if it cannot. We want the driver to keep authenticating it until the user space tells us explicitly not to. So if the user space sets it to desired, we need to keep trying until unless it tells us, okay, you can't do it. Let's just leave it be, and I'm disabling it. So how does it work? The flow. The user space comes in, sets the content protection to desired. At this point, drivers like, okay, time to go to work. It becomes a messenger of sorts between your sync and the security engine, where it talks to both to get the authentication up between the source and the immediate downstream device. Once the link or once the authentication over that link is up, it sets the user's or the content protection property to enable, and it's supposed to then send a u event to the user space to let the user space know that it can transmit the actual high quality data that it needs to, or the high quality content it needs to. One peculiar thing I mentioned here was immediate downstream device. So the policy is that, and this comes from the HDCP spec itself, that the source is only responsible for taking care of authentication with its immediate downstream device. So if the immediate downstream device is a repeater, let's say, it's the repeater's job to make sure that any other device that is connected to it is authenticated by it, and that keeps on going for every layer. The only thing that the source will do is wait for its immediate downstream device to get all the authentication done with its leaf devices or leaf nodes. And once that is done, the downstream device is supposed to signal the upstream device, or that would be the source, saying that it's done with the authentication, and it sends us a message which normally contains your key and a list of all the devices that are downstream to it. So we get an idea of the topology where we can check if it's not exceeding a maximum number of depth and width when it comes to the topology. So yeah, that is one thing I would like to mention. How does the disablement work is user space needs to set the content protection property to undesired, at which point the driver will disable your HDCP and then not try to re-enable it until again user space sets it to desired again. So some things to keep in mind is the driver is going to be a messenger, which means that it won't be aware of any real master keys or any keys that are being generated. No, neither the session key, neither the master key, neither the locality check key that it requires. It is just going to be passing on values from the security engine firmware to the monitor via aux transactions or I2C transactions based on which connector you are using. But it in itself won't have any algorithm implemented within it. It's just going to be like a sort of arbiter telling it what to go where, and basically being the middle man for everything. Next is there is a periodic sanity check that the driver needs to keep doing, which basically means that once your HDCP authentication is up, you need to make sure that it stays up. So let's say if it goes down in between, then you really don't want the hardware to be like, okay, it's down, but it's still enabled. We feel it's enabled, but at that point, it's vulnerable to an attack. So we don't want that to happen. So if that's the case, if it goes and does a sanity check and it finds out that okay, HDCP is not enabled at any point, it has to send a U event to the user space and tell it that HDCP is not up. I'm trying to get it up. Wait for me. And okay, I already talked about the revocation list. So basically, drivers another job is to basically make sure that any device that is on the revocation list does not get authenticated. So there's a separate step for that. So now let's talk about what is there in upstream in terms of HDCP. So we have our whole code with HDCP 1.x implemented as DRM helpers, and some of it is implemented within the drivers itself. With the help of Google and the rest of the community, we got this merged. But with HDCP 2.x, the whole implementation is within individual drivers. So that is one work that is there for the future we need to do. And HDCP 2.x also was when we introduced the UAPI property called content type, which told us which type to enable. So now you see these flow charts. This is basically how if user space sets property to desired, so what a enablement flow would look like. So if anybody wants to go to the code through the code later, I think this would be a good starting point. So I can explain that at this code flow takes into account that the monitors are all HDCP2 capable and nothing goes wrong at this point. So yeah, let's begin. So when user space sets the property to desired, we call on Intel HDCP enable, which will internally call Intel HDCP2 check capability. Now there it basically goes to its own connector callback. So if it's a DP connector, it goes to its own DP implementation, and if it's an HDMI connector, it goes to its own HDMI connector implementation, where it goes talks to the monitor using the either the aux or I2C and checks the capability if it is HDCP2 capable or not. Then it comes down. If it is HDCP2 capable, then it goes calls HDCP2 enable. At this point, there are three major steps that happen here. The first one would be your creation of master key and the storing of this master key, both in the monitor side and the sources side. So that happens. Then there is this locality check that needs to happen, which makes sure that all the devices that are connected to your source are in close vicinity. So how it does that is it just sends a packet downstream and makes sure that packet is uh, acknowledged within a certain milliseconds. Next is there is also this step where we need to wait for the downstream repeater, if it is a repeater, to authenticate everything downstream to it and reply with the topology back to us once everything is authenticated. Once that is done, we let the link, we signal that okay, HDCP is up. So at this point, we have two functions that we need to call. So that is we queue a delayed work, which is Intel HDCP check work, and we also update. We call Intel HDCP update value. So what do these two functions do is let's have a look at HDCP update value, which calls Intel HDCP prop work internally, which again calls DRM helper, which is DRM HDCP update content protection, whose job is to update the content protection property state. So here we set it to enable because our authentication is done and we are up. So this updates that. It also calls sends a U event to the user space telling that the authentication is done and you can call me, or you can start sending sensible content. So that's what Intel HDCP update value does. Then you have Intel HDCP check work. So this is the periodic sanity check that we need to make sure happens. So internally it calls Intel HDCP check link, which has connector specific callback, which basically makes sure that how if the link that was encrypted is still encrypted or not. And this needs to be done every few milliseconds. How it's checked depends on which connector is being used. So you can have a look at how that needs to be done over the DP spec, DP or HDMI spec for HDCP, which is different. So they both have their own connector specific implementations. And let's say you do detect that the link is actually down now. So it's this function's job to get everything up and running. So it makes sure that HDCP is re-enabled. And once that's done, it again reschedules a job for later to again run the same cycle of things every check. I mean, every few seconds. So now we come to PAVP. So PAVP would be your protected audio video path. So now while HDCP made sure that everything within the hardware is secure and nothing and there is no hardware in between that makes sure that is copying pirated stuff with you. PAVP makes sure that everything in the software is okay and there is no software trying to snoop in on your content. So this is the safe environment that DRM talks about. So DRM makes sure basically that, or PAVP makes sure that there is no other screen capturing app that is running on your OS that can have a look at what encrypted content you are actually trying to consume. So this it does this by creating a session, and the session once it's created, it directly goes through the hardware, and the hardware directly sends it to the display rather than having it being sent through the uh, OS, and this is done on a per plane per surface basis. So let's say if you have PAVP enabled on a certain surface and you take a screenshot, it basically will be static for the enabled PAVP session, but the rest of the screen will come out as you see it. So how does HDCP and PAVP work together? So while HDCP is making sure that there are no uh, hardware in between that can capture your data, PAVP makes sure there is no software in between, and together they work in a nice symphony to make sure that you have an end-to-end encryption, and there is no one in this whole box or in this whole environment who can pirate your content. So challenges and downsides. The main challenge would be your increase in cost. So you have your cost of implementation. You need your developers who understand the code and who can code this. You have your firmware chip certification that you need to do. Then you also have your computation and for encryption and decryption cycle. That also increases the cost in a way, right? And next is older platforms. So one of the challenges, like, you need to make sure all the platforms that are using your standard are all updated at the same time, because if there is any device that has not updated to the latest standard, it won't be able to do its authentication perfectly and may end up with a black screen. Then if a standard is broken, like HDCP 1.x was, you cannot revoke it without affecting legitimate users, and that's a really big problem with content protection. Next is implementing content protection like HDCP sort of goes away from our open source policy, where we want all the code to be in front of us and everything needs to be open source. But with this, you have to implement the majority of the algorithms within the firmware or hardware, and that sort of becomes a necessary evil, so that it's not easy to reverse engineer all these algorithms. But yeah, that is one downside. Upcoming plans is HDCP 2.x is internal. Most of it is internal to each driver. We would want to pull in the common code and put it in the DRM core, which is a good amount of work, because we'll need to go and search for everyone who has implemented this and what is the common code there. Then you have your then the next work that we are doing is basically trying to create an HDCP tool which helps with testing your HDCP. We do have IGT tests that basically enables and disables HDCP, but we do not have a tool that lets you, to begin with, it does not work as a video player for us without where we can do multiple hot plugs and see if we add a new monitor, how does it actually behave. So yeah, we have this work that is going on. This is being coded by Santosh, my colleague from Intel, and being reviewed by me and Ankit. And what next for HDCP? So recently HDCP 2.3 got in support for 8K. So with this trend, I'm seeing it will support higher resolution going forward. Next thing I see is there are new contents that have become more accessible. So AR VR content that has started becoming more accessible, and with that, I'm seeing you at some point it will want content protection there too. So HDCP will need to evolve to take into account these new contents into picture. So some references, if anybody was interested in reading the HDCP specs, they are available in on the first link here. You have it separate for DP and separate for HDMI. And then if you are just interested in general content protection and all things related to content protection, there's this really good chapter that I found here in this book. So do have you can go through it. And if you are interested in code, you can just have a look at these last three links, where DRM HDCP helper will give you all HDCP 1.x helpers that are required. Intel HDCP.c and Intel HDCP DP, Intel DP HDCP.c will give you an implementation of how the HDCP flow happens for us and what are the connector specific functions that we require to implement HDCP end to end. With that, any questions? I think I'm done with my presentation. So, I mean, it's going to be a little tough to ask me questions, but yeah, since this live is a little problem. I mean, any questions? Okay, thank you everyone. Okay, so there's one question.
Yeah, okay. Hi, thank you for the talk. I just wanted to ask, do you know about the current status about discussions within, I don't know, the MESA, graphic, FDO community, and how far we actually want to have stuff like this in our common protocols, etc.? Does the question make sense?
Okay, there are some technical difficulties with the chat in the Jitsi instance. But give us maybe a second. All right, I think it's easier to take the questions offline, perhaps in the Matrix channel. Yeah, because otherwise it's a bit difficult replaying them on Jitsi. Okay, well, let's thank the speaker again.